Hello Internet! Glad you tuned into my new episode. Today we are talking about another design method to create furniture handles using mesh modeling based on a primitive shape. Our goal is to create a furniture handle that is recessed or milled into the wood, as you can see here in the example. In this video I will show you how I proceeded from the first design in Blender to 3D printing to milling out the pocket for the finished part with my Makita router. We will go through the most important steps. Maybe at a certain point I will go over some of the very details of the mesh fitting more quickly because it's repetitive and boring for you. Each model is slightly different, and if you know the basics, you should have no problem achieving similar results to mine. And as always, if this video is helpful for you and entertaining, please keep in mind to give me a like and subscribe. Leave a note in the comments to give me some ideas how I can improve my videos. It would be nice to get some feedback, and it motivates me to create more content like this. But enough of the words, let's have a look into the design process. In the first step, we set the measurement system. In my case, the metric system with millimeters as the unit. In the grid settings of the 3D view, I set the same scale to get millimeters as grid unit. With this, I can now absolutely align my model or geometry to the 3D grid in the orthogonal perspectives. To do this, grid snapping with absolute positioning must be activated. Here again the keyboard codes for the navigation as a reminder. Let's start with the base object. As the basis, I take a suitable primitive shape, a cube. I enter the necessary dimensions directly in the dialog item Transform Dimensions dialog. This changes the scaling of the object, but the object scaling can have influence on different Blender functions and modifiers, so the scaling should be applied early in the modeling process. Then I prepare the base model and add additional geometry as needed. For later modeling, it is necessary to add additional geometry subdivisions to be able to work with the mesh geometry and to model the desired shape. I switch to edit mode for this and use the edge subdivide function with a subdivision of 10. I did use a lower resolution with fewer vertices because I want to design a rough shape by hand. Later I will use the subdivision surface modifier and smooth the model, or use one of the smooth modifier functions, and then work on the details and the final shape. To do this, I select the area for the pocket and use the inset faces function. This gives me some additional geometry to work with. Then I select the inner area of the faces so I can rotate and reposition the selected faces. To rotate the faces from a given point, I set the cursor to the upper front edge and then use the cursor as the active pivot point. By switching to the orthogonal perspective and the grid in the 3D view, you can position and align the geometry with excellent accuracy. Depending on whether a finer or coarser subdivision is needed, by zooming in or out, centimeter, millimeter or tenth of a millimeter distances can be used. For the pocket, I add additional divisions with the loop cut tool. Use the key combination Ctrl R. I extrude these to the inside and the pocket is roughly defined. With the faces activated and selected, you can precisely position them using the grid view. Change to the orthogonal perspective and use the grid view in combination with snapping and absolute positioning. Voila, we have the basic shape. Now we have the basic model ready, but I want to round the edges and make the shape more fluid. I use the subdivision modifier. To avoid too much rounding and to keep the dimensions, I need to insert additional geometry. Now I select all the vertices that belong to the pocket and add them to a defined vertex group. Later on I can use this vertex group to use it with a smooth modifier to smooth out the geometry. To get a better overview of the outcome and the final shape of our model, we can manipulate the matcap settings. In the viewport shading settings, I can change the matcap setting so that I can better evaluate the change of the model geometry and their outcome on the overall model surface. Therefore, errors in the models become quickly visible. The detailed work and shaping of the model can be a very time-consuming process. So to make it faster, I split the model and use the Mirror Modifier. This way I only have to worry about one side of the model. I can get the vertices on the center line to be on a plane of the x-axis. In case there are holes in the middle after applying the Mirror Modifier, you can centerline the vertices on the x-axis using the SXO key combination, so there are no holes caused by the mirror function. Important here is the active pivot point settings. I use the 3D cursor as a reference for the position of the selected vertices on the x-axis. Here I use the 3D cursor as a reference for the position of the selected vertices on the x-axis. In addition, I now have the possibility to model the handle pockets of the model in more detail. To align the vertices on the x-axis, for example if you have a hole like here, you can use the key combination SXO, maybe in combination with the cursor as active pivot point. So place the cursor on the x-axis where you want to align the vertices to and use the key combination then to align them. You can also do it manually in the orthogonal perspective, or you can select the vertices and use the transformation item dialog to set the vertices to a defined X position. I don't want to have any support structure here at this point in the model, because if I remove the support structure it will leave some visible marks and it's hard to get rid of them. I use general curves and make sure that the steepness of the surfaces remains as low as possible. Since a 3D printer using the FDM process cannot print in the air, or let's say the so-called bridging is very limited, I have to prepare my model for 3D printing. In the slicer program, such as Cura, I can later define from which steepness of a surface a support structure should be added. Using the 3D printing toolbox add-on in Blender, I can test the model and select surfaces that are too steep. Typical settings for me are between 62 and 75% slope of the surface, depending on the printer and material. To get a nice result, I make a lot of small corrections to the model and use, among other things, the merge function to delete unnecessary vertices from the model. I clean up the geometry because the subdivision surface modifier algorithms like a very symmetric and equalized model geometry to get the best result. And I also use the bevel tool from the mesh modeling tools to get nice bevels, and in combination with the subdivision surface modifier I get these nice rounded edges. I add or clean up faces to clean up the geometry, and I also use the mesh cleanup functions. You should get rid of overlapping vertices or faces and check for non-planar or concave n-gon faces, and to correct them using the mesh cleanup functions in the edit mode. This is also important for the 3D printing process later on, because the slicer might have different problems if your model geometry has some defects. I add a video here that shows the preparation and the use of the cleanup functions. And you can use the dissolve function to delete any unnecessary geometry in your model without affecting the overall shape of your model. I designed two different models, one with a rabbet and an outstanding rounded handle, and one flat model with a rabbet. But let's stay with the first version for now. The model has not to be printed as one solid block. I create additional cavities to reduce the printing time. After that, I export the model to STL format to test the slicing in the Cura slicer program. Here are the typical file export settings to create an STL file. The STL file contains all the surface or hull information of your 3D object that is necessary for the slicer program. Now I can check the individual print layers and the print model for errors. I slice the model and switch to the preview view of Cura. So for what I see, the print looks good. I see no unnecessary support structure, I see no holes, so therefore I say it's fine. And looking at print time using the default settings, it will take round about 7 hours. Maybe we can improve this later on and decrease the print time a little bit. I will show my settings in the Cura slider for my PLA Plus material and my Creality printer later in the video. You can slow down the video or stop the video to see the individual settings. The basic guidelines for me are, for this example, outer 2mm layer height, 1 to 2mm wall thickness, 215 degrees nozzle temperature, 50 degrees bed temperature, and 35% infill. In addition, I created another model with a stepped top edge. This can be used to hide and slide inaccuracies during the milling process. Here you have to take care to get sharp corners, especially in the inner corner edges. For this purpose, I add additional cuts with the loop cut tool, or I use the knife to get sharp edges. Edges can then be moved into the corners with the key combination GG. This function can be used to slide edges along other edges. Some fine detail work was also necessary in this model. I found holes that I deleted using the merge function, and I also added additional vertices or faces where it was needed. The steps that I processed here are very similar to the one that I already processed in the previous model. Therefore, I do not explain this in detail. Just have a look in the explanation of the previous model. Also here I corrected the slope of the pocket geometry to get rid of any support in the pocket. The models are printed on my Creality printer CR10S4 using the FDM 3D printing method. The layer height was about 2 mm. Looking at the final 3D printed object, it still looks a little bit rough, but with some sanding, priming and painting, you can create very nice results. More about this in the upcoming videos, but I can show you a very similar example that I produced around Christmas time. I will add a link here in the video. If you are working with a model without a rabbet, then you have to work very precisely and pay attention to the radius of the cutter, which must match the radius of the corner edges of the model. Otherwise you will get ugly holes at the corners. Therefore I think the version of the handle with a rabbet is better. For demonstration purposes I used the router to cut a handle into an acacia board. I used a small Makita router with a 12 mm groove cutter and an 8 mm shaft. I did not use a router fence during the milling and guided the router free in my hands. With 3 to 5 mm removal per routing pass, this was no problem, plus the wood had short fibers, which made the job a lot easier. Afterwards I reworked with the chisel and cleaned the corners a little bit. Sense and purpose of an own handle design is of course not to save money, but the possibility to use your own individual design. There are no limits to your imagination. And hopefully I could inspire you to try it on your own and create your own furniture handles. That was it for today. I hope it was entertaining and maybe helpful for your projects. Please remember to like the video and subscribe if you want to see more from me. It also motivates me to produce more content. If you have any ideas for improvement or questions regarding my content, please leave a note in the comment sections and I will do my very best to answer your questions and have a look onto your proposals. That's it for this video. Thanks for watching and bye.